Now, hopefully you're already starting to maybe see a couple of issues with this, okay? One kind of issue is that we see a trinomial, okay? Now, it's not to say that we couldn't technically rewrite this as 1 or as 1 minus everything else. So I could write it as 1 minus negative x squared plus 4x minus 2, right? And then that would be the thing that I end up raising to the power of n. But it turns out that I would have a very difficult time coming up with my interval of convergence for that. It wouldn't really be a good form because it doesn't just look like x to some power. It looks like a trinomial to some power. So that's not a very good method of doing this, okay? So we're not going to do that. Instead, we're going to try to do something to the function to make it look a little bit better. So does anybody have any ideas about what we might do?
Complete a square?
Complete the square? Okay, you would if you can't factor, but this one right here you can factor, so there's no point in completing the square. Because notice in this case, I could just rewrite it as x minus 1 times x minus 3. But then we still have an issue. Now, I do want to mention, completing the square would be beneficial. But that would imply that we would have some center other than 0. Whenever we can help it, we'd like to have the center at 0, but sometimes we just want the center to be somewhere else. So if we complete the square, then it might look like something like, I don't know, x minus 2 quantity squared plus 4 or something. And then we could write it in the form 1 minus something, right? And that would be good, but that would give us a center at x equals 2. So whoever said that was a nice choice, but we're going to look at this a little bit different as well, okay? And that is one choice, and I probably should do that one as well, okay?
Would you use partial fraction decomposition?
Yeah, there we go. So why don't we drive partial fraction decomposition here? Because if we could do that, wouldn't that look like a over something plus b over something else? And now look at those denominators. They're both linear, and I could end up turning them into very basic power series, okay? So that's why we're going to set this 1 over x minus 1 times x minus 3 equal to the decomposed fractions, okay? So that means that 1 is equal to a times x minus 3 plus b times x minus 1. And now we can solve by plugging in 1 and 3. So if we let x equal 1, and we let x equal 3, then we know that this is going to cancel if x is equal to 1, which gives me a is negative 1/2. And if we let x equal 3, then this would cancel, which would mean that b is equal to 1/2. Okay. All right, well, great. Well, let's go ahead and see what that implies then. That must mean that this function is the same thing as just writing f of x equals negative 1/2 over x minus 1 plus 1/2 over x minus 3. And now we can see that we could rewrite this in order to fit into the power series, the basic power series form that we're familiar with. Okay, so the way that we're going to do this is that we're going to rewrite the left one as negative 1/2 times 1 over x minus 1. But I want it to be 1 minus x. And so what's something that I could do here? Or I
Maybe
guess
you
I
can
could,
multiply it by -1.
yeah, if I multiply it by -1, then that just changes the direction. So that's why I could really just rewrite it as this. So 1/2 times 1 over 1 minus x. And now notice that this one right here looks exactly like the form of the sum from n equals 0 to infinity of x to the power of n, with a 1/2 out in front. Well, now if we go to the second one here, okay, we go to the second, I have a couple of choices as to how to create this power series. And I know that some of you are thinking, well, why don't we first of all just rewrite this as 1 over, and then we get -3 plus x as a starting point. And then some of you are like, well, why don't we just rewrite this as 1 minus, and then we get 4 minus x. And that gives us -3 plus x, right? So it is 1 minus something. But I'm going to tell you what the big issue is with doing it this way in this particular circumstance. This would imply that I am, in this case, centered at 4. But notice that over in this one, I'm centered at 0. So when I'm trying to rewrite a function that I've decomposed, then that means that I need to combine them eventually into one power series, not two separate power series, but one power series. And in order to do so, they have to be centered at the same location. So that's why we're not going to rewrite that as 1 minus 4 minus x. Instead, we're going to rewrite it as by dividing by -3. So we're going to divide top and bottom by -3 here. So let me go ahead and erase this. Give me a sec. Okay, so this now gives us plus, and instead we're going to divide top and bottom by -3. Okay, so we have plus 1/2 times. And now if I divide the denominator by -3, then that gives me 1 minus x over 3. And on top, that gives me -1/3. And look at the benefit of doing this. The benefit is that now I don't see any difference associated with this term, so I know that it's still going to be centered at x equals 0. I don't see 4 minus x or something like that, right? So I could still factor out this -1/3, okay? All right, so we see that f of x is equal to, well, I could bring this sum of n equals 0 down to infinity of 1/2 times x to the power of n. And now over here, I could see that this is minus 1/6, because I just factor out the -1/3 to here. And now if that's a 1, I know that I have the sum from n equals 0 to infinity. Only now I have x over 3 to the power of n. And what I've now technically done is I have created a power series for this function 1 over x squared minus 4x plus 3. A series to where I can actually approximate this function with a polynomial. But I'm still not technically done because it's not a single sum yet. So that's why we're going to combine this into a single sum by remembering a property of summation that allows us to just add or subtract the arguments to combine it into a single sum. Okay? So that's why this is going to turn into the sum from n equals 0 to infinity of 1/2 x to the power of n minus 1/6 times x over 3 to the power of n. And again, I'm going to continue to say that that is technically the power series. But you got to realize that if I were to try to start expanding this, I'd have to start plugging in 0 to here and to here, simplify, and then combine them. And then I'd have to plug 1 in to here and to here, simplify and combine them. And then I'd have to plug in 2, simplify and combine them. So that's why we're going to simplify this again so that it becomes, how can we rewrite this as a sum from n equals 0 to infinity of a sequence times x to some power. That's what we're looking for. So let's just continue to break this down a little bit more. Well, I can distribute this n right here to the top and bottom. Okay, so I get the sum from n equals 0 to infinity. When I distribute that x to the n, I'm going to get an x to the n over 1/3 to the n, or I'm sorry, x to the n over 3 to the n. So I could factor out an x to the n from both of those terms. And that's going to give me, from the first term, I'll have just 1/2. From the second term, I'll get minus 1/6 times 1/3 to the power of n, or 1 over 3 to the n. Okay. And now I'd say that that's probably pretty good. Okay, because at this point, I could possibly simplify a little more by pulling out, say, a 1/2, combine terms a little bit more. But the point of this is we're pretty much done, because this is now the C sub n, which is telling me my coefficients. Okay. So our goal oftentimes is, whenever you see some rational function, is to do partial fraction decomposition, because we're going to be able to, assuming that we don't have irreducible quadratics, we're going to be able to combine it into a single power series that indicates what each of the coefficients are going to be and what each of the powers of x are going to be. Right on.
So if you were to find the interval of convergence,
it's a great question. What would the interval of convergence be here? Okay. So if we were to find, if we were to really apply the ratio test, then that's what we would end up doing. But the trickier part about this is that you've got to find the interval of convergence of both. Yeah, thank you. I should have mentioned that as well. Okay. Turns out that we've got to find the interval of convergence of this series and this series separately. So we could technically do the ratio test on this, but I'll tell you right now, that's going to be a pain in the ass. So instead, I'm not going to do that. And I'm just going to go back to here, and we're going to find the interval of convergence of 1/2 x to the n. So that means that for the first one, okay, that would mean that x has to be between -1 and 1. And then for the second one, x over 3 has to be between -1 and 1. Which means that one interval of convergence, the interval of convergence for the first one is just -1 to 1, while the interval of convergence for the second one is -3 to 3. So how do you think I find the interval of convergence for the difference of the two of them?
subtract them, but that isn't.
Well,
The
not
average
quite.
of them?
It can't. The interval of convergence for the sum of two of these, if this right here is only convergent between -1 to 1, then by taking the difference of the two, I still know that this can't be anything more than the interval from -1 to 1. So I can't choose the larger of the two, because then this value right here would give values that don't work in this integral or in this sum. So that's why when you're finding the integral of, or the interval of convergence for a sum or difference of functions, it turns out that it is the lower or the smaller of the two. This is the interval of convergence for the whole thing. Okay.
Is it also because in our final power series we have x to the n? It's like because we don't have an x to the over 3 to the n, we don't really have to worry about that other interval?
Well, not quite, because if I had an x over, if I had x over 3 to the n, then I would see that the interval of convergence is -3 to 3, right? But if I were to distribute this to simplify, wouldn't that 3 to the power of n move into the sequence in the front? So I can't ever find the interval of convergence just by using the final sum, because then that would mean if every one of these can be written as x to the power of n, then that must imply that every interval of convergence is -1 to 1. But that's just not true. So you've actually got to find the interval of convergence. You got to find the interval of convergence by using the original series before you end up separating and simplifying and getting that c sub n out to the outside. I'll restate that because maybe that wasn't quite clear. If I were to be able to simplify every power series to x to the power of n, which I typically am, then that might imply to you that -1 to 1 is always the interval of convergence. But it's not, because if it happened to have an x over 3 to the power of n, like this, then I realized that the interval of convergence would be -3 to 3, not -1 to 1. But notice that 3 to the n right here, that 3 to the n, kind of got lost because it merged together and to create the sequence that showed the coefficients. So instead, we always have to take the interval of convergence from the original series, which is also what we noticed back here on this last one that we did. Okay, was that, as Dylan mentioned, you could have, instead of using the ratio test, you could have just used the original series, right? But look at what the original series was. It was the thing that was raised to the n. Later on, notice how that ended up becoming something different. It transformed. And if we'd never accounted for that 4x squared, that 4 ended up joining the sequence in the front. So if we only accounted for here, then we'd say, well, the interval of convergence is -1 to 1, okay? When in fact it was actually -1/2 to 1/2. Okay?
And for the radius of convergence, you would pick the lower of the two?
Yeah, it's always based off of what the midpoint of the interval of convergence is. So if the interval of convergence here is -1 to 1, then obviously the radius of convergence would just be 1. Since it's centered at 0. Okay. Centered at 0, spread 1 unit to the right and 1 unit to the left. Cool. All right. We're going to see something now that's pretty mind-blowing. Let's take a look at another example real quick. Find the series expansion, or I guess we could say find a power series representation of f of x equals 1 over 1 minus x squared. All right, well, look at how this is a little different than the last one, because this one is already 1 minus x quantity squared. And so there's no way for me to do a partial fraction decomposition because it's already, now I could say a over 1 minus x plus b over 1 over 1 minus x squared, but a would be 0 and b would be 1. So I can't really decompose this. And the issue that I'm having here is that there's this exponent up here that I have to deal with somehow. And it doesn't quite look like 1 over 1 minus x because of the fact that that denominator is being squared. So right now, the way that it looks, I can't really find a good power series representation of this. So now we want to look at something a little bit different real quick. So we're going to revisit this in a minute. Okay, and we're going to look at this from a different perspective. Okay, so if I have the series of x to the n, right? Let's look at this term by term to see what we get. We get 1 plus x squared plus x cubed, and so on. Everybody go with that? Now we know that that right there is also going to be equal to all right, we know that this is going to be equal to 1 over 1 minus x. Agree with that? All right, so that's our basic definition of our standard power series. All right, well, let's see what happens if we were to do a little calculus. What if we were to differentiate this power series? If we were to differentiate that power series, and the power series has this expansion, then wouldn't that mean that I would really just be differentiating term by term? Okay, well, let's go ahead and see what that becomes. Okay, that becomes 0 plus 1 plus 2x plus 3x to the 4th, and so on, right?
Isn't it squared? 3x squared?
Yeah, I don't know. I'm in integration mode right now. 3x squared, thank you. So 0 plus 1 plus 2x plus 3x squared, right? Well, let's go ahead and see what happens as well when I differentiate the function that represents that power series. So apparently, if I have a power series, then I can create the expansion, and then I can create the function that describes that. So that must mean that if I try to differentiate the sum notation, the power series itself, that I really am just differentiating term by term. So what exactly does this become then?
Negative ln of 1 minus x plus c.
Not quite. We would use, we're differentiating, not integrating, right? So we're finding the derivative. So let's do the quotient rule, right? So we start with the bottom, 1 minus x, times the derivative of the top, minus the top, times the derivative of the bottom, all over the bottom squared.
Couldn't we just have turned it into 1 minus x quantity to the negative 1 power and
Sure,
then
you could have done
differentiate
that as
that way?
well. Absolutely. You could have done the chain rule at that point if you wanted to do that instead. Yeah. So let's simplify this and see what we get. 1 over 1 minus x quantity squared. Whoa, wait a second. It looks like that right there was the power series that I was just trying to find an expansion for. So it looks like this is the derivative of 1 over 1 minus x. Now, there'd be no way for me to notice that, obviously, okay? But we do see that it turns out to be the derivative of 1 over 1 minus x, which is great. So let's go ahead and see if we could come up with a formula that would essentially tell me what the expansion of this would be. So what would this formula look like?
The sum of n equals 0 to infinity of n times x to the n minus 1.
Close. But keep in mind that this is a 0, and this is a 1, and this is a 2, and this is a 3. So let's try to rewrite that as a sum. The sum from n equals 0 to infinity. Okay. Any ideas here?
Would it be n times
So it's definitely going to have n as the coefficient. The subscript is 0, 2 is
and
a subscript, 3 is a subscript.
yeah, then something to the n minus 1.
And then x to the, well, it
And-
looks like it's 1 less than the subscript, 1 less than the subscript, 1 less than the subscript. So sure enough, it looks like this is n times x to the n minus 1. Anybody's mind blown yet?
Mine.
Couldn't we have just taken the derivative of the function inside the sum?
Oh,
That's
that's so
the
weird.
rule.
That is it. Oh my god.
That's the power rule. So that must mean that if I want to differentiate a power series, all I really need to do is find the sum from n equals 0 to infinity of the derivative of x to the n. I didn't have to go through this whole process of expanding and so on. So all I really had to do was recognize that the power series, the derivative of a power series, is the sum of the derivatives. So I could really differentiate this term to term, which is why this ends up becoming 1 over 1 minus x squared. So wait a second, what does that imply? It implies that the sum of this power series is equal to the sum from n equals 0 to infinity of n times x to the n minus 1. I don't have to rewrite it, it's already there. Okay. Okay, well, hold on a minute. Let's go back then and see how we would do that in a practical sense. So essentially what we're able to do, and I'm going to demonstrate something else in a minute here, is that even though I may not be able to come up with a power series expansion of this function directly, if this has a derivative, okay, if this has a derivative or an integral that's going to turn into a nice form, then I'm going to do it. Okay? So what we're going to do here is we're going to say, let's go ahead and find the derivative of 1 over 1 minus x squared. Let's try that. Okay? Let's find the derivative of 1 over 1 minus x squared. Okay, well, that's the derivative. Okay. All right, so this is the derivative of 1 minus x to the negative 2. And that means that it's negative 2 times 1 minus x to the negative 3 times negative 1, which means that this derivative is 2 over 1 minus x cubed. And that's worse.
Yeah, that didn't really help.
So that didn't help. So it doesn't have a derivative that's very nice to work with as a power series. So why don't we look at its integral then? Okay. So why don't we go ahead and now look at it in another way and say, what if we were to find the integral of 1 over 1 minus x squared dx? Well, if I were to rewrite that, then that becomes the integral of 1 minus x to the negative 2 dx. If I'm going to do this, then I would have to use u substitution here. So the derivative of u is negative 1. So I'm going to multiply the inside by negative 1 to get what I need, and multiply the outside by negative 1 as well. Okay, so now I'm just integrating u to the negative 2 du. Okay, well, the integral of u to the negative 2 is u to the negative 1 times negative 1 times negative 1, which is simply 1 over u. Oh my God, look at that. Okay, so it looks like this function is the integral of a nice, or the integral of this function is a nice power series. So let's think about what that then tells us. Okay.
Would we include the plus c or no?
We don't need to include the plus c, no. So what we're basically just trying to do at this point is recognize that this function is equal to the integral of 1 over 1 minus x squared dx, which means also that 1 over 1 minus x squared is the derivative of 1 over 1 minus x. They're inverse processes. So I'm basically just saying that if I take the integral of this, then I get this, which must also imply that if I take the derivative of this, I get this. And
But
so
does that mean that we take the integral of the power series now?
And so therefore, we're not taking the integral of the power series, we're taking the derivative of the corresponding power series. So let's, hold on one sec. Okay. So essentially what we're doing then is saying, well, great, this had a nice integral, so that means that 1 over 1 minus x squared is the derivative of this nice power series. So that means that I can rewrite 1 over 1 minus x squared as the derivative of the sum from n equals 0 to infinity of x to the n. But as we just derived down below, we just saw that the derivative of a sum is the sum of the derivative. So now all we have to do is differentiate x to the n, and therefore 1 over 1 minus x quantity squared has a power series expansion as the sum from n equals 0 to infinity of n times x to the n minus 1. And there's my expansion. So essentially what we're doing here is just recognizing that if we're able to turn if we're able to differentiate or integrate, and I'm going to show you that in a minute as well, if we're able to differentiate or integrate in order to get a certain, to get a better form, then we're going to do so, okay? Is anybody, I'll give that a minute to sink in. So any confusion on what we essentially just did here?
Yeah, I just think it's really cool.
It is very cool, isn't it? So again, the point of this, by the way, there was no way for us to really put this here. There wasn't a way for us to really put that directly into the form of a power series, 1 over 1 minus something, right? So instead, we said, maybe its derivative or integral has a nice form that we could turn it into. So we tried it, and it worked. And so it turned into the derivative of some nice power series. And so that means that we can bring the derivative to the inside. Cool.